Welcome! Today, we'll explore an exciting problem from LeetCode, number 22, generate parentheses. This problem challenges us to generate all combinations of valid parentheses for a given input. Let's dive into the intuition and approaches to solve it step by step. The goal of this problem is to generate all possible combinations of well-formed parentheses given in pairs. A well-formed parentheses string means that every opening parenthesis has a corresponding closing parenthesis, and the pairs are properly nested. For example, is well-formed because all the pairs are balanced and nested correctly, while is not well-formed because it has an unmatched closing parenthesis. The input to the function is an integer n, where n represents the number of pairs of parentheses. The output is a list of strings, where each string is a unique valid combination of well-formed parentheses. The challenge lies in ensuring that all generated combinations are valid and that no duplicates are included in the result. Now, let's look at an example where n equals 3. This means we need to generate all valid combinations of well-formed parentheses using exactly 3 pairs. The output contains the following 5 combinations, and in the first combination, all 3 pairs are fully nested. In the second, the first pair is nested, while the second and third pairs are interleaved. In 2 pairs are nested, and the third is separate. The combination has the first pair separate, while the second and third are nested. Finally, shows all 3 pairs as separate and sequential. These combinations illustrate the different ways parentheses can be arranged while maintaining proper balance and nesting. When n equals 1, the output is straightforward because there is only one valid combination. This is the simplest well-formed parentheses string, where one opening parenthesis is directly followed by its closing parenthesis. Now, consider the case where n equals 2. Here, there are 2 valid combinations, and in the first combination, both pairs are nested. This means the first pair of parentheses fully contains the second pair. In the second combination, the 2 pairs are sequential, with each pair standing independently. These examples demonstrate how the number of combinations grows as n increases, and they highlight the importance of proper nesting and balance. The constraints of the problem specify that n can range from 1 to 8, and the number of valid parentheses combinations increases exponentially with n. For instance, when n equals 1, there is only one combination. When n equals 2, there are 2 combinations. For n equals 3, the number grows to 5 combinations. By the time n reaches 4, there are 14 combinations, and for n equals 8, there are 1,430 combinations. This exponential growth highlights the need for an efficient algorithm to generate all combinations without redundancy. Additionally, it emphasizes the importance of ensuring that the solution scales well as n increases within the given constraints. Finally, let's consider edge cases. For the minimum input, where n equals 1, the output is always, as there is only one possible way to arrange a single pair of parentheses. At the maximum input, where n equals 8, the output includes 1430 combinations. This underscores the need for an efficient approach that can handle large outputs without running into performance issues. There's no need to handle invalid or empty inputs, as the constraints guarantee that n is always between 1 and 8. Another key consideration is symmetry. Every valid combination must maintain proper nesting and balance between opening and closing parentheses. By adhering to these constraints, we can ensure the solution is both correct and efficient. To tackle the generate parentheses problem, we first considered the brute force approach, which involves generating all possible strings of length 2n composed of n opening parentheses and n closing parentheses. The intuition here is straightforward: create all combinations and then filter out the invalid ones. However, there are some key observations to note. For n pairs of parentheses, the total number of combinations is 2 to the power of 2n. Among these, a valid string is one where, at any point in the sequence, the number of closing parentheses never exceeds the number of opening parentheses. While this approach is simple to understand, it has significant trade-offs. The time complexity is n*2*2n, because we first generate all combinations and then validate each one. The space complexity is also high due to the need to store all combinations. Given these inefficiencies, this method becomes computationally expensive and impractical for larger values of n, which is why we decided against using it. A much more efficient strategy is the backtracking approach, which focuses on constructing only valid strings of parentheses directly, rather than generating all possibilities and filtering them later. The key intuition here is to use recursion to build valid strings step by step, ensuring that we only add opening or closing parentheses in a way that maintains balance. The main insight is that, during the construction of the string, the number of closing parentheses can never exceed the number of opening parentheses used. Starting with an empty string, we recursively add either an opening parenthesis if we haven't yet reached the limit of n, or a closing parenthesis if it won't violate the balance condition. The recursion ends when the string reaches the full length of 2n. This approach is highly efficient because it avoids the overhead of generating invalid strings altogether. The backtracking approach has several notable trade-offs. In terms of time complexity, the number of valid sequences corresponds to the nth Catalan number, which grows as O, 4 to the power of n/sqrt, n. Since constructing each sequence requires O, n, operations, the total complexity becomes O, 4 to the power of n/sqrt, n, *n. On the space side, the recursion stack depth is O, n, and the result list requires space proportional to the number of valid sequences, or O, c, n. Despite these complexities, backtracking is still the preferred approach because it avoids the inefficiency of generating invalid strings. We also briefly explored a dynamic programming strategy that leverages the recurrence relation for Catalan numbers. This method involves breaking the problem into smaller subproblems, where each valid combination can be formed as a, b, with a and b being valid combinations for smaller values of n. While this is mathematically elegant, it introduces additional overhead in managing subproblems and is less intuitive to implement compared to backtracking. Ultimately, we chose the backtracking approach as the optimal strategy for solving this problem. It strikes the perfect balance between simplicity, efficiency, and clarity. By generating only valid strings during the construction process, we eliminate the computational overhead of filtering invalid combinations, as required in the brute force method. Compared to dynamic programming, backtracking is easier to implement and avoids the complexity of managing subproblem dependencies. The recursive nature of the algorithm is both intuitive and practical, making it accessible for moderate values of n. While it's true that the number of valid combinations grows exponentially with n, this growth is unavoidable for any approach. Backtracking handles it as efficiently as possible by focusing solely on valid sequences. This combination of computational efficiency, straightforward implementation, and scalability makes backtracking the ideal solution for the generate parentheses problem. To solve the problem of generating all combinations of valid parentheses for a given number of pairs, n, we can break the task into clear steps. First, we start with a brute force approach. The idea is to generate all possible strings of length 2n that consist of exactly n opening parentheses and n closing parentheses. To achieve this, we use recursion. At each recursive step, we either append an opening parenthesis or a closing parenthesis to the current string. We continue this process until the string reaches the required length of 2n. This ensures that we explore every combination of n opening and n closing parentheses. By generating all these combinations, we lay the groundwork for identifying which ones are valid. Although this approach produces many invalid strings, it guarantees that no valid combination is missed, making it a comprehensive starting point for the solution. Once we have generated all possible strings of length 2n with n opening and n closing parentheses, the next step is to filter out the valid combinations. A string is considered valid if its parentheses are balanced. To check this, we use a helper function that traverses each string and maintains a counter. The counter starts at 0 and is increment for every opening parenthesis encountered, and decrement for every closing parenthesis. If at any point the counter becomes negative, it means there are more closing parentheses than opening ones, making the string invalid. Additionally, for the string to be valid, the counter must return to 0 at the end of the traversal, ensuring that the total number of opening and closing parentheses are equal. By applying this validation step, we can discard the invalid strings and collect only those that satisfy the balance constraints. While this approach is not the most efficient due to the initial generation of invalid strings, it does guarantee correctness by thoroughly checking each candidate. The brute force approach gives us some important insights about the problem. First, all valid strings must have a length of exactly 2n, as each valid combination consists of n opening and n closing parentheses. Second, valid strings must satisfy two key balance constraints. At no point during the string should the closing parentheses outnumber the opening ones, and by the end of the string, the total number of opening and closing parentheses must be equal. These constraints ensure the validity of the parentheses structure both during the construction of the string and at its completion. To explore all possible strings, we rely on recursive generation by appending either an opening or closing parenthesis at each step. During this process, we use a string to build the combinations, a counter to track the balance of parentheses, and a list to store all valid combinations once they are verified. Together, these data structures and operations allow us to systematically generate and validate potential solutions. Instead of generating all possible strings and filtering out invalid ones, we can optimize the recursive approach by directly avoiding the creation of invalid strings. This can be done by enforcing constraints during recursion. Specifically, we only append an opening parenthesis if the count of opening parentheses is still less than n. Similarly, we only append a closing parenthesis if the count of closing parentheses is less than the count of opening parentheses. By enforcing these rules, we ensure that every string generated during the recursion is valid, eliminating the need for a separate validation step. Regarding complexity, the time complexity of generating all combinations is O(2)(2n), but with filtering and optimizations, it reduces to O(C)(2n)(n), where C(2n)(n) represents the number of valid combinations, which is a Catalan number. The space complexity is O(n), as the maximum depth of the recursive call stack is proportional to the length of the string being constructed. These optimizations make the approach more efficient while maintaining correctness. This implementation generates all valid combinations of parentheses strings for a given number of pairs n using a backtracking approach. The generate parenthesis function initializes an empty list result to store all valid combinations. It also defines an inner function backtrack, which performs the recursive backtracking. The backtrack function takes three parameters: current, the current string being built, open_count, number of opening parentheses used, and close_count, number of closing parentheses used. The base case for recursion is when the length of the current string equals 2*n, meaning the string is complete with n pairs of parentheses. At this point, the string is appended to the result list. The recursive logic ensures that at any point 1. An opening parenthesis can be added if the open_count is less than n. 2. A closing parenthesis can be added if the close_count is less than the open_count. This guarantees that the generated string is always valid because it prevents unmatched closing parentheses. The recursion starts with an empty string and 0 counts for both opening and closing parentheses. The backtrack function explores all valid combinations by making decisions to add either an opening or closing parenthesis at each step, while adhering to the constraints. Once all possibilities are explored, the result list, containing all valid combinations, is returned as the output of the generate parenthesis function. This solution leverages the efficiency of backtracking to prune invalid states early, ensuring that only valid combinations are generated. The time complexity is proportional to the Catalan number 4n, which is the count of valid parentheses combinations for n pairs. The space complexity is determined by the recursion stack, which can grow up to 2*n in depth. Here, we begin by defining a class called solution and implementing the function generate parenthesis. This function takes an integer n, which represents the number of pairs of parentheses we want to generate. Inside the function, we initialize a list called result to store all the valid combinations. Then, we call a helper method named backtrack, passing it the result list, an empty string to build the combinations, and counters for open and close parentheses, both initialized to 0. We also pass the maximum limit n, which ensures we generate exactly n pairs of parentheses. The heavy lifting is done in the backtrack method. First, we handle the base case. If the length of the current string equals 2 times n, it means we've successfully created a valid combination, so we add it to the result list and return. Next, we check if we can add an open parenthesis. If the number of open parentheses is less than n, we make a recursive call, appending an open parenthesis to the current string and incrementing the open count. Similarly, we check if we can add a close parenthesis by ensuring the number of close parentheses is less than the number of open ones. This maintains the balance of parentheses while building the combinations recursively. Finally, the recursive calls in the backtrack method will explore all possible combinations of open and close parentheses under the constraints defined, ensuring only valid combinations are added to the result list. Once all recursive calls have completed, the generate parenthesis method returns the result list containing all the valid combinations. This approach uses backtracking to efficiently generate the combinations while pruning invalid ones early in the process. The use of recursion ensures that every possibility is explored in a structured manner, and the constraints on open and close counts help maintain the correct sequence of parentheses throughout. To solve the problem for n equals 1, our goal is to generate all well-formed parentheses combinations where there is exactly one pair of parentheses. The only valid result here is a single set of parentheses. We start by calling the generate parenthesis function with n equals 1. This initializes an empty result list and begins the recursive backtracking process with an empty current string and both open_count and close_count set to 0. At the first step, we add an open parenthesis, incrementing open_count to 1, and proceed by calling the backtracking function again with the updated state. In the next step, since the current string is still shorter than 2*n, we add a closing parenthesis. This updates close_count to 1, and we make another recursive call. Now the length of the current string equals 2*n, so we append this valid combination to the result list. Finally, we backtrack to earlier states, exhaust all possibilities, and return the result. The output for this case is: for n equals 2, we need to generate all well-formed parentheses combinations, which include two pairs of parentheses. The possible valid combinations are, and. We begin by calling generate parenthesis with n equals 2, initializing an empty result list and starting with an empty current string, along with open_count and close_count both set to 0. The process starts by adding an open parenthesis, incrementing open_count to 1, and making a recursive call. In this new state, we add another open parenthesis, bringing open_count to 2, and proceed further. Now that open_count equals n, we can only add closing parentheses. We add 1, incrementing close_count to 1, and make another recursive call. Then, we add another closing parenthesis, reaching close_count equals 2 and a valid combination, which is added to the result list. After backtracking to try other possibilities, we return to the state where current is, and add a closing parenthesis instead. This leads us to explore the second valid combination. With current as, we can still add more parentheses. Starting with an open parenthesis again, we increment open_count to 2 and make a recursive call. At this point, we add a closing parenthesis, resulting in the string, and incrementing close_count to 1. From here, we add one more closing parenthesis, completing the string, and reaching a valid state where both counts equal n. This combination is appended to the result list. After finishing all recursive calls and backtracking completely, we find that the final result for n equals 2 is. This demonstrates how the backtracking algorithm systematically explores all valid paths by adding parentheses according to the constraints of the problem. For n equals 3, the number of well-formed parentheses combinations grows significantly. Here, we need 3 pairs of parentheses, and the valid outputs include, and. The backtracking process follows the same principles as before. Starting with an empty string, we recursively add open parentheses until open_count equals 3. At that point, we begin adding closing parentheses until close_count also equals 3. For example, one path might be adding 3 open parentheses to form, then adding 3 closing parentheses to complete. Backtracking allows us to explore other possibilities, such as closing earlier to generate combinations like, or splitting pairs to create strings such as. By systematically exploring all paths, we eventually find and store all valid combinations. The final output for n equals 3 is. To analyze the time complexity of the generate parenthesis function, we begin by considering the number of valid combinations and the cost of generating each one. Each valid combination consists of exactly n open and n close parentheses, forming sequences of length 2n. The total number of such combinations is defined by the nth-Catalan number, mathematically expressed as c, n, equals, 1/n plus 1, asterisk, 2n choose n, or equivalently, 2n. /n. Asterisk, n plus 1. Catalan numbers grow approximately exponentially, with the growth rate approximated by c, n, is almost equal to 4 to the power of n, /sqrt, pi asterisk n. Additionally, the cost of backtracking to generate each valid combination is proportional to the sequence length, which is O, n, since we append one parenthesis at a time to construct strings of size 2n. With this in mind, the total time complexity is the combination of generating all valid sequences and the cost of constructing each one. Given that there are approximately c, n, combinations and each takes O, n, time to generate, the total time complexity is O, c, n, asterisk n. Substituting the approximation for Catalan numbers, this evaluates to O, 4 to the power of n/sqrt, n, asterisk n, which simplifies to O, 4 to the power of n asterisk sqrt, n. Now, let's consider the space complexity. The main contributors are the recursive stack space, the storage for results, and temporary strings during recursion. The recursive stack depth is proportional to the length of the current string, which is at most 2n, giving a maximum stack space of O, n. The result list stores approximately c, n, strings, each of length 2n, requiring O, c, n, asterisk 2n, space, which simplifies to O, 4 to the power of n asterisk sqrt, n. Finally, temporary strings created during recursion also consume O, n, space, but this is insignificant compared to the storage for results. Combining all the factors, the total space complexity is dominated by the storage for the result list, which is O, 4 to the power of n asterisk sqrt, n. To put this into perspective, let's compare this backtracking approach to a brute force method. A naive approach would generate all 2n possible strings of length 2n and then filter for validity. Since checking a single string for validity takes O, n, time, the overall time complexity for brute force would be O, 2n, asterisk n. This is far less efficient than backtracking because 2n, grows significantly faster than c, n. By pruning invalid combinations early, the backtracking approach avoids generating and checking all possible strings, reducing both time and space complexity. Additionally, backtracking ensures that only valid combinations are constructed, resulting in substantial optimization over brute force. To summarize, the time complexity of the generate parenthesis function is O, 4 to the power of n asterisk sqrt, n, and the space complexity is also O, 4 to the power of n asterisk sqrt, n. This is a dramatic improvement compared to the brute force approach, where the time complexity is O, 2n, asterisk n. The backtracking method achieves this efficiency by pruning invalid combinations early and limiting the generation of sequences to only those that are valid. This makes backtracking exponentially faster and more space efficient, making it a highly effective solution for generating valid parentheses combinations. When solving the generate parentheses problem, there are a few common mistakes to watch out for. First, not validating the order of parentheses. This means your algorithm might generate combinations where closing parentheses exceed opening ones at some point, which violates the rules of valid parentheses. Remember, at any stage, the count of closing brackets should never surpass the count of opening brackets. Neglecting this leads to invalid outputs and wasted computation. Another frequent issue is defining the base case incorrectly in recursive solutions. For instance, you must stop the recursion only when both the number of open and close parentheses reaches 0. Without this, the recursion might either run indefinitely or terminate prematurely, resulting in incomplete solutions. Lastly, in backtracking approaches, failing to prune invalid paths early can be costly. For example, exploring the option to add a closing parenthesis when there are fewer open parentheses remaining is unnecessary and adds to the computational burden. Pruning such paths is crucial to maintaining efficiency and avoiding redundant recursive calls. Now, let's focus on handling edge cases and efficiency. Overlooking special scenarios like n equals 0 can lead to errors. For n equals 0, the output should be an empty string, not null or undefined. Similarly, for very large n, the number of valid combinations grows exponentially, and failing to account for this can result in significant performance issues. Another critical aspect is being mindful of time complexity. Brute force approaches might seem acceptable for smaller inputs, but as n increases, the exponential growth makes them impractical. Recognizing this is essential for designing scalable solutions. From an interview perspective, this problem often tests your ability to identify patterns, particularly the connection to backtracking and dynamic programming. It's important to articulate how you prune invalid paths to optimize recursive calls, which demonstrates your ability to think critically about efficiency. Additionally, discussing scalability is key, explaining how you'd handle larger values of n and considering optimization techniques like memoization can set you apart. Finally, you should be ready to compare approaches like recursive backtracking and dynamic programming, weighing their trade-offs in terms of clarity, space, and efficiency. This problem is closely related to several others, such as LeetCode 20, which focuses on validating parentheses, and LeetCode 301, which involves removing invalid parentheses. These problems share the underlying principles of maintaining valid parentheses order, making them great practice. Turning to alternative approaches, dynamic programming offers an interesting solution. Here, you use a DP table where DP, I, stores all valid combinations for I pairs of parentheses. While this avoids redundant calculations, it can be more space-intensive than backtracking. Another approach is iterative construction, where you build combinations by adding, or, step by step while ensuring validity. This method avoids recursion and is less prone to stack overflow for very large n, but it can be more challenging to implement because you need to manage the state explicitly. Each of these approaches has its strengths, and understanding when to use them is a valuable skill. Finally, the Catalan number formula provides a mathematical perspective on this problem. Using this formula, you can directly calculate the number of valid parentheses combinations for a given n. This is especially useful for theoretical analysis and understanding the problem's exponential growth. However, the trade-off is that this approach doesn't generate the actual combinations, it only tells you how many exist. While not as practical for solving the problem directly, this insight can deepen your understanding of the problem's complexity and serve as a useful tool in discussions about its mathematical properties. Great job! To summarize, we tackled the generate parentheses problem by leveraging backtracking to efficiently generate valid combinations. This approach highlights the importance of pruning and recursion in problem solving. Keep practicing, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!